Yeah, good evening. I would like to show you how am I solving a higher order polynomial, and then I mean a higher order higher than 2, provided that, as in this example, I have a higher polynomial with 0 points. I mean, you cannot dissolve a higher order polynomial if you don't have 0 points. And yeah, in some cases that's how polynomials come. So if you have a higher polynomial that has no 0 points, then this method you cannot use unless you lower the whole polynomial or elevate the order polynomial to where it crosses the x line. And well, sometimes you can encounter difficulties in approaching, because if it doesn't look nicely, that not every 0 point, if it crosses the line, if you manage to fix it on a crossing the x line, that it has no 0 points at all, or shows lesser 0 points than the order of the polynomial. In that case, you cannot use this method. But in any other case that yes, you have a polynomial that indeed crosses as much times as the order is, then you can solve it in the way I'm going to show you right now. I took an arbitrary, from which I don't know the 0 points, except then that I can see it's approximately 5.4 or something like. It's minus 5.44, minus 2.1 or 1 or 2, something like that, and 2.05 or something like that. That's based on what I see, but it's not accurate. So I'm going to determine in a far more accurate way what the exact points here are. And what I did, as you can see here, I constructed a picture of it, and here are the points. I enlarge it for you. Alright, so that you can see it. Because the resolution of my camera is not that big. Here what I did is I optimized the zooming in so that I get a clear picture on the graph. And what I did is I took in this case I started with -6. Well, this is the polynomial. And I want to know the 0 points, which were, just as I mentioned a moment ago. Well, these are the parameters, the constants, and I calculated that here. So what I did, I did some increments of, you can see here, of, well, I'll put it down here, 0.0075. This is the increment, as you can see here in the line, but maybe it's not, you can see it not clearly enough because the resolution of my camera. But this is that's why I put it here. This is the increment that I used. I use this increment because it's so I can get a clear picture of my graph. I optimized the picture for the graph, and based on that, I use this increment. Okay, I will zoom a little bit out. Now, the first crossing the 0 line is approximately, this is -5, and this is approximately -5 point, what is it, 4 or 5. So I'm going to look over there, and there I'm going to start my work. So I'm going to increase the over here, and I'm going to look to -5.4 approximately. Yeah, here it is. Okay, so here it's going from minus to plus. Yeah, you can see where it crosses the 0 line. Now, okay, I have to zoom back out. What I'm going to do, by the way, is I'm inserting here, insert. This is all in Dutch, so I have to translate sometimes. Here it says insert, and I'm going to insert a graph, and this one, this type. Okay, like that. I'm going to zoom out so you can see it more clearly. Yeah, to 100. I will zoom in to 100%. So this is, I constructed a zoomed in portion of the graph, and I'm going to, and I will show you later why. What I'm going to do is here set the axis, so like this, 2, 5, and make the line, the 0 line, a bit more subdivided. Can zoom in on that. Here, so I made increments of 0.0025 for the x-axis line. And what I'm going to do, I'm going back to 100%. This is 100%. And what I'm also going to do is measure the increments. In this case, with a centimeter line. And I'll show you why in a moment. So, okay. I'm going to analyze the graph a little bit, stretch it a little bit out, stretch it a little bit, and the other. And in a moment it will become clear why I'm doing this. So, I'm not going to tell you, I'm going to keep it as a nice surprise. What I'm basically doing is setting these lines, a little teeny weeny back. I hope that. No, I hope that's enough. So I put the increments on. No, it's a little too far. So I put my zooming in of this whole thing to 100%. I'm going to far a little back. And there's a reason why I do this, as you will see in a moment. No, I don't need you. No. A little more. I hope this is fine. Yeah, this is every increment what you here see is now, as you can see from my measuring thing, it's 1 centimeter. Okay, 1 centimeter. So what is I zoomed into 100%, and so every increment here is 1 centimeter. Maybe with my, so it's pretty simple, but as you put a ruler. Okay, now I'll go back. What I'll also do is, and I'm going to show you, add a trend line. And of course, we're approaching a higher polynomial with a second order polynomial, a parabola. And in this case, I take the equation into the graph and the r squared into the graph. You can see that here well. Here it appears. This is the, and it looks very good. Then I double click on it, and here I go back to number. This is for the 1,000 steps of 1,000, and I increase the number of digits to 20, and then I close the whole thing. So this is what I get. A very large, and I copy these numbers. Control copy. I put them here and stick like that. There. Well, what I'm going to do now is, as you can see, up until the 20th, I'll zoom in for a moment. 20th digit, r squared is 1. 1.00000, etc. Okay. What I'm going to do next is copy this one, the whole formula. Copy. And because I have 3 constants, A, B, and C, because it's a polynomial of a second order, a parabola. And what I'm going to do is I'm going to select these constants in such a way that I have pure the constants. So I'm going to remove everything which is not part of the constant that I'm required, and I'm selecting. These are a couple of zeros, so I don't need them. And the last one. So that's minus 180 something, and I don't need a whole bunch of zeros that I'm never going to use. Okay, these are my numbers I'm going to work with. I'm going to increase the numbers in such a way that, well, a whole lot of zeros appear. I don't need them. That's enough. Enter. And next thing, what I'm going to do is calculate the solutions. x1, in which I'm going to use the positive thing of the ABC formula, and x2, which is the minus. Well, you all know the formula for solving a second order polynomial or parabola, and that is plus minus b, this is b, plus, and that's where this plus comes from, and then the square root. Well, in Dutch we call it wortel, and this is a Dutch language computer, so I have to use the Dutch version of it, but you can take the square root or root. Usually it's SQRT, but in Dutch it's wortel, W-O-R-T-E-L, of, and then again B times B minus 4 times A times C. Well, the basic high school level ABC formula. Bracket closed, and dividing the whole thing by 2 times A. Okay. Bingo. Well, there you have it. As I said, the first solution is minus 5.38 something. I'm going to increase the number of digits until there appears a lot of zeros, which I do nothing with. Okay, and that's it. Okay. Well, for the completeness, I will also copy this. Copy and paste it over here. Okay. But I have to restore something because everything moves down, and I'm not interested in that, so I have to restore that a little bit. So, and this, now it really matters. And I have to change this for the plus for a minus, and then it's complete. And this happened to look to minus 3.1418, approximately minus pi. That's a coincidence. Okay, now I'm going to calculate what the result is if I take this number, which I just found. I hope you can see well. And I put it in my cubic formula to see whether I get a good approximation of the number that I'm looking for. So I'm going to take the formula, which is this one, and take it close to 0 point. Now let's take this one. Control copy, and going back, all the way back, and put it here, and copy again. Well, that's fairly good. This is minus 2.675 times 10 to the minus 8. And so we have an error. There is an error of relative to 0, 0 of plus that times 1,000,000 ppm, parts per million, which is fairly good. I mean, it is, but it's below below 1. So plus that times 1,000, and I get the relative error to 0 in ppb, parts per billion. So the error is 26.75 parts per billion and something. Well, okay. Now let me remind you that this is of course a non-zero error. Of course you want as close as possible to 0, preferably 0 itself. But let's put this in perspective. Now I'm going to zoom out. Oh, sorry, let's zoom in, zoom out. To back again to 100%. And that's why I measured this whole thing in centimeters. Because if you consider it, I mean, if this graph is in centimeters, and you consider, now I'm going back to zoom in again. You have to put this in a correct perspective. An atom, a hydrogen atom, is 5.29 e to the minus 11th meter. Now, what I did here is all in centimeter. So that's why I put the centimeter. That's why I used this one, and put the graph all in centimeters. Okay, so I have to divide this error, plus this, divided by 100, which is in centimeter. And if you compare that to the hydrogen atom, which has a dimension of this, 5.29 times 10 to the power of minus 11 meter. And you put this in centimeter, as I have constructed the graph. This is a meter. So I have an approximation of plus this divided by the dimension of the atom. I have an approximation in meter of approximately 5 times of 5 hydrogen atoms. So if you put 5 hydrogen atoms next to each other, then I have the relatively error to 0 of 5 hydrogen atoms. Well, which is fairly good. I mean, for a relatively simple approximation, that's good. 5 hydrogen atoms, and for most practical purposes, this is more than enough. Okay, let's see if I can get an even better approximation. But then again, I have to increase, or I have to go back to here, to my graph, and see if I can improve my zooming in. So I have to, what I will do, because computers have the tendency to round it off, so minus 5.4, and then I will zoom in even more. I will reduce this 0.0075, and I will reduce it to 0.001. So 7.5 times better. And I will copy that until I find the 0 point. Well, not here yet. I did something wrong. I have to copy it. Minus and only here you get, okay, here you get, here it crosses the line. Here. Let's see if I can get, here you have 4 points. You have to have a minimum of, because it's a second order approximation, you have to use a minimum of 3 points. Well, in this case, it's approximately spread. In here is somewhere the 0 line, and it's minus 0.011, and here's minus 0.12. So it's somewhere in the middle here. So I take, in this case, because it's symmetric, I take these points as to try to approximate the whole thing. Let's zoom out. Zoom out, I said. And take another graph, delete this whole graph, delete, and construct a new graph. Okay. Construct a new graph, there it is. Put this away, and approximate it again. Adding a trend line, polynomial, second order polynomial, put the equation and the r squared in it, and see, I want to see the number 20 digits. Of course you can do it as much as you like, but I prefer 20 digits, and there it is. Okay, let's see if we can get a better approximation of the whole. Copy it again. Putting it here. Oops, there it is. I'm taking again, copy. Copy. And again, I get my constants from it, delete. Same procedure over and over again. Now let's see if I can get, oh, come on, do me a favor. Minus 90. Yep. These are slightly different numbers, of course. That's what you expect. And it should be a better approximation because we zoomed in, actually. Okay. Make the digits, number of digits bigger, yeah, so you can see them. And I copy the whole procedure here again. So let's see what happens. Of course, I hope it's getting better, but from my experience, that's not a guarantee. But in this case, it is. And it's a very good one, actually. It's at the same level as no, it's even smaller. It's 100 times, well, yeah, almost 100 times better approximation than a hydrogen atom. So if you see here, These are the numbers. Let me zoom in. I didn't practice this in front of it, so it was a surprise for me as well as for you. Now the plus 1 divided by the number. So now the hydrogen atom is 114 times bigger than the approximation. We found here, this is the number what we're looking for. I will zoom in for a moment. Based on that, I have an error of 4.63736 times 10 to the minus 11 centimeters, because we did a whole graph in centimeters, which is in meters times 10 to the minus 13. A hydrogen atom is 5.29 to the minus 11, 10 to the minus 11 meter. So actually, the error is about 114 times smaller than the hydrogen atom. So we're getting closer to the size of a nucleus of a hydrogen atom, and this is very good actually. So it's 4.64 times 10 to the minus 5th ppm, which is 0.04637 ppb, and if we do that times 1,000, then it's pp trillion or whatever. It depends on what well, this is it's 10 to the 6th, 10 to the power of 6. ppm, pp million, 10 to the power of 9, this is 10 to the power of 12. So the accuracy of this method is with, how much did I use here? It's only an increment or what is it? Well, if you subtract these two, and you have an increment of 1,000 only, so 0.001. And based on that, you get an approximation which is 114 times smaller than a hydrogen atom, and it approaches the size of a hydrogen nucleus, which is far better, of course. So you see that with a relatively simple way, you can find the 0 point very accurate, very accurate. So this is my first 0 point, which is on the plus. Mark it green, and so I can construct my whole third or higher order polynomial, because what I'm going to do now is use this polynomial, these constants, copy them, and I'm going back to the top. Now we'll zoom a little out, and I put them here, these constants, because that's my first parabola. So, and now I can construct, based on this, I can construct my first parabola. And the 0 point I also going to come y first parabola p, first p. So I get this is my y times again times a plus that times that plus this is my parabola. constants. So, and now copy it and to the rest. This is my first parabola. And you will see that if I add it to this graph, I extend it to the C. Look, there it is. So now you see that I have added a parabola based on what I found. And I'm going to as well get the 0 point, which I'm very pretty proud of it. Control copy. This is my 0 point, first 0 point, which is, I will put the number there. This is my first 0 point. Well, let's put a smaller font. Now, this is my first 0 point, in which I get an error in the order of 10 to the minus 11 centimeters, or 10 to the minus 13 meters, which is absolutely marvelous good. Of course, it's a parabola, and this is a third order, so further away from the 0 point, the graph deviates from each other, as you can see here. The parabola is going back to 0 quicker, and the third, but that's not what I'm interested in. I'm interested in this 0 point here, and that's what I found here. Very, very, very accurate on the level of less than a 100th part of an atom, a hydrogen atom. Hydrogen is one of the smallest atoms that we know. So for practical purposes, this is a super good approximation. Now I can do this, construct this for the whole. I can do this for all the 0 points, and I will do that, and I will come back with the move where I go on with the movie. So I will pause now and later continue with it. Okay, see you in a moment. I will do the rest myself. I'm not going to tire you with the rest of it. Okay, see you in a moment. For the second point, I also used the same first approximation with an, here it is, these numbers I used. Here you have it. These numbers I used for approximate the second point where the line, the cubic formula crosses the 0 line. Well, that's here. And here, and this is the formula I get, quadratic formula. It's not as good as the first one, as you can see. The r squared is a couple of 9s and then 3/8 something. But then nonetheless, that's the same. The increments here are as well 0.0075, and in a moment I will increase or decrease the increments 7.5 fold, so that you get 0.001. But you can see here that this is the solution. These are the parameters. This is the parabola, and I use these constants for that. And this is my finding. In this case, this one. I will make it green. It's this one. This time it's the minus solution. And I compared it again with a hydrogen atom, which is in this case 13 times bigger, 13.4 times bigger. So it's 13.4 hydrogen atoms next to each other. That's the accuracy in this situation, in centimeters. What is it? Okay. Yeah. So it's a pretty fair, good first approximation, but let's see if we can improve it. And I will be back with you in a moment again. I'll do the same thing as I did before in the first thing, but I'm not. I will save you a lot of time watching this video. See you back in a moment. Now here I have used an increment of 0.001 instead of 0.0075. So the increment is here 7.5 times smaller, and this is the numbers I get, and I will take, I try to be as symmetrical as possible, so I use around 0, so that I get a fairly good approximation. I use these numbers. I use the minimum amount of numbers that I can, or points that I can use is 3, so I will use these 3. This is the most symmetrical, around 0, crossing the extra line, x-axis. But I try to do that as symmetrical as possible. But with a minimum of 3 points, if I have only 2 points, I cannot construct a parabola. And so I will use these 3, and try to use as minimum as possible points, because well, that's better for the approximation. That's my experience. Let me put it that way. Okay, let me construct a second. Here. And I'll be back with you in a moment. Well, you can see it anyhow, by the way. Why not? Nothing to hide for it. So. Adding a trend line, polynomial, second order. I do the same thing over and over again. 20 digits, and today, there it is. And copy the numbers. Control copy, close this, and putting it here like that. Well, I'll be back in a second with all the thing, and I'll show you the details. See you in a moment. Okay, here I'm back again. I constructed the approximation, and indeed it's better than before. This was the first approximation with we have approximation that is 13 times bigger than a hydrogen atom, and here it's what is it in meters? It is what is it? A quarter of it is 14 times smaller than the diameter of a hydrogen atom. And this is my second point here. This is my second point. Yeah. So the approximation is on the level of less than a hydrogen atom, which is, well, like I said before, for most practical purposes, it's perfect. Perfect, good enough, anyhow. Okay, this is what I wanted to share with you. This is what I wanted to share with you, folks. This is the way how I solve higher order polynomial equations. And oh, by the way, I forgot. What I can do is finish this whole thing and show you the end result. And that is what I'm going to do right now. It takes a little bit more while, so I'm not going to tire you with that. But I will show you the end result of it. Okay, see you in a moment. Also here for the third point, I found a very accurate approximation in the first step. I'm going to do an extra step so it becomes even more closer and more accurate. But in this case, it's 8.8 times bigger than a hydrogen atom. Okay, I'll keep you informed when it's more accurate and the whole construction of it. So see you in a moment again. Yeah, and again I improved the approximation. What I did is again, I'll show you here. Just increase or lowered the approximation, the graph, for this amount. So from, let me put it, zoom in on it. This was the increment, the first increment, from which we have this number and this approximation. And the only thing I did is changed the increment from 0.0075 to 0.001. So 7 times better increments. And what that delivers is that we have now that it's about, what is it? 16 times more, so 16 times smaller than a hydrogen atom, which is this. So it's a very good approximation again. So 0.315 ppb, as you can see, or 315 ppt, 5 trillion, or at least 10. These names depend on what system you apparently use. But it's actually 315 times 10 to the 12 part per trillion. So, which is then again this amount better. So it's what is it? Let me put it like this, and a number, regular number, ordinary number. 0.06 times smaller than the diameter of a hydrogen atom, which is fairly good. It's very, and I assume you can increase the accuracy to higher levels. I'm sure of it, but I'm not going to show you right now. But I'm sure of it. Okay, I'll finish it and I'll show you the end result in total. See you in a moment. Okay, now I found all 0 points, which are not here in this area, and these are the same 0 points as I will have shown you. This is my final 0 points, and these are the 0 points that are in the smaller than hydrogen atoms accuracy, and I will use them to construct this is what I get. Zoom out from all the 3 parabolas. This. And here, I can enlarge this one. Let's enlarge it. So, this is the thick blue line is the cubic equation where I started with, and I approximated each 0 point. I approximated it with a parabola. This one, the green one here, is going through here, and this one, the purple one, shows this one. As you can see, it's a very good approximation in the 0 points. Of course, the further you go away from the 0 points, the more it deviates from the cubic formula, which is logic. That's what you expect. But now I found here the 0 points, that are these. I'm going to zoom in on them so you can see them. These are the 0 points, which you also can see very clearly from the graph. Actually, if you look at the graph, then you can see that it's correct. And now I'm going to construct a final graph in which I take it like this: plus x, which is in this case minus 6, minus the first number. Close the bracket. Now I have this. X minus the first 0 point. That's this one. Times, open bracket, x, 16, minus the second point. That's this one. Here, D13. Okay, close the bracket, times 16 minus the third 0 point, and that's basically the whole formula. And as you can see, these numbers correspond. And it should. I mean, this is the original formula, which, to remind you, is this one, is here. As you can see it. X to the third plus 5.5 to the power of times x to the power of 2 minus 3.854 times x minus 24.1. That's the original formula. And we go back to where the 0 points are here. So basically you see here the same numbers, which that's exactly what you expect here. Minus 18.976 minus 18.976. Okay, that's what you expect. This number is here. I'll mark it for you in yellow. Is the same number as this one. And that's what you expect. Let's put it in yellow as well. Yeah. Okay. And this should be done for all numbers, but first I have to fix the whole thing, because otherwise it's going wandering around. So I have to place dollar signs with it. And anybody who works with Excel knows that I have to fix these numbers, otherwise it grows crazy. And then, well, I'll put them blank again. And I'll copy it. Oops. Let's see if yeah, it's all the way down and up here. Okay. Now, I'm going to zoom out and I'm going to put this new final graph into this one, into the big one. And I should see the same graph again. What I, by the way, will do, I'll show you in a moment what I will do. So, add, name is this one, yeah. X values, yeah, let's put it that way, 1, 5, 6, yeah, and then that one is Y. Yeah. 1, 5, 6, 8. Bingo. Okay. And there it is. It's a lighter blue. Well, because the graphs are overlaying, so you cannot see the difference, what I will do is add the number of 1 to it, plus 1. So I lifted up one unit, and I'll copy this all over the place. Oops, and there you get it. Wow, it's not so distinct. I'll add 2 or 3. Let's do 3. Let me see it more better. Or no, 5. Okay. So here now you can see it. There's a clear distinction. I added 5 for each number. I added 5, and that's why it's running parallel, but 5 higher, 5 lifted up. I will make it thicker so that you can see it more clearly. Yeah. And put it away. Yeah, bingo. So this is the same line as this, but then lifted 5 up. So you see there's a very good, very good very good way of getting the same graph, but then with the 0 points. These are the 0 points. And this is just the same thing, but as you can see here, you can see that I added 5. So this formula, and I added a 5, and that's what you see in graph being in total lifted up 5 points. But you saw if I take it away, then you will not see the difference between the two. I will remove the 5, and then copy it and zoom out again, and you will see no difference with the original formula. If I add 5 again, plus 5, you can see clearly the distinctive. Boop, there it is. So you see that this is a very good way in getting the 0 points, which are here, from a higher order polynomial. Well, okay, this is what I wanted to share, how I am doing it. This is what I want to share with how I am doing it, how I reconstruct a higher order polynomial based on with an Excel sheet, and you can get an approximation of very good approximations, even smaller than the hydrogen atoms. And well, for the most approximations, for the most applications also, that's more than enough. And if you want more, if you zoom in more, then it will become even more accurate. So this is endlessly. Okay, thanks for watching. This is what I wanted to share with you, how I do it, how I did it, and yeah, use it as you like. Okay, thanks for watching. Hasta la vista. Bye bye. See you next time.